As strange as they are, black holes are a product of the familiar universe of stars and gravity. They have their genesis in a type of enormous star called a red supergiant. It is 10 times heavier than our Sun, yet it will burn itself out in a fraction of the Sun's lifetime. Deep inside, the crush of gravity sends temperatures roaring above 1 billion degrees. Helium and carbon fuse into heavier elements: oxygen, silicon, sulfur. Then, the star implodes under its own immense gravity, sending a shockwave roaring out. The star digs itself deeper into space travel and now goes supernova in a violent explosion. What's left is a dense core of subatomic particles, a neutron star, only about 16 kilometers across.
It's so dense that a teaspoonful of neutron star matter would weigh about 1 billion tons. Eventually, the gravitational pressure will be so large that the neutrons themselves will be crushed and there'll be nothing left to stop the collapse.
A black hole is born. It's 1 million times the mass of the Earth, but compressed so tightly, it literally exits the known universe.
Now, the effect of that mass is still in our universe. The mass is still here in that it's causing this fold in space that goes all the way down. It's become a hole. The best way to look at it is, if you stick your finger down in there, you ain't getting it back.
We know exactly what effect a black hole is going to have on its environment, on the stars in its vicinity, on the gas that wanders a little too close. So, will we ever see a black hole? No. But that's not what's important here. What's important here is we can see its paw print.
In search of a black hole's paw print, Eric Becklin is on a lifelong quest to probe the center of our galaxy. The Milky Way is a giant spiraling disk of over 100 billion stars. Our Sun is about halfway out, in the peaceful suburbs. Becklin is headed to the galaxy's most exciting and most violent zones. But to make the final leg of the journey, he would need help. So he turned to a rising star in astronomy. Andrea Getz believes that the key to finding a black hole at the center of our galaxy lies in tracking the stars that buzz around it.
For about 3 decades or so, there has been this question of whether or not our galaxy harbors a supermassive black hole at its center. And the key to answering this most definitively is to watch stars at the center of the galaxy orbiting.
Getz's team set up at the newly built Keck telescope on the summit of Hawaii's Mauna Kea volcano, the largest telescope ever built.
Our view to the center of the galaxy is absolutely superb. Our ability to position stars at the center of the galaxy is like somebody in Los Angeles seeing somebody in New York be able to move their finger like this, okay, just 2 centimeters. That's the precision with which we can measure something that is 26,000 light years away from us. Madeline, we're ready to go?
The conclusive experiment to be done that really demonstrated there was a black hole was to follow the orbits of individual stars very, very accurately and with the highest precision possible.
But the stars in the center of the galaxy were not the only thing Getz and Becklin had to keep track of. Another group, working in the mountains of Chile, was hot on the same trail, led by Reinhard Genzel from Germany.
This guy here. Yeah. It's a little too dense to be just a random collection. We suspect that in the galactic center there may be hiding very massive black holes. To really be sure that there are black holes, we have to go in there as close as we can, so we can make measurements really good enough now that we can say it must be a black hole.
Both teams wanted to be the first to prove that our galaxy harbors a supermassive black hole, but Gensel and his team had a 3-year head start. The amazing precision of Keck is the ace in the hole for Getz and her team. Mark Morris is a veteran of the Galactic Center search.
The German group had already started to make headway on the Galactic Center even while we were deciding to pursue this. So we knew that in a head-to-head competition that as long as they were using the small 2.2 meter telescope that they were using compared to our 10 meter telescope, that we would blow them away.
Bright speck on the top of this inset. That's the star which really has given us the essential clue for the black hole.
It was certainly high excitement, but on the other hand, we would have to compile like at least 5 years of data before we could see the stars move.
But what kind of cosmic monster was pulling the stars along?
This is our roadmap, and that's the center of our galaxy. There's a large cluster of stars that are orbiting the center of our galaxy. Basically, the way this experiment works is you take an image, you see where all the stars are, and then you come back sometime later and you take another image and you look to see if they've moved. So the second time we took an image, we knew we were golden, that those stars had clearly moved.
The first order of business was to see how large the object is, to weigh it by measuring its gravity.
So we have the black hole here, and then the more massive it is, the more pull there is. The more pull there is, as it gets close to the black hole, the faster it goes. And we are measuring the speed of these stars. That's the key to getting the masses, measuring the speed of those stars.